Differentials can be applied to error analysis or uncertainty propagation or error propagation. We often use this in physics labs or chem labs or biology labs where the things we've measured aren't precise. We know they have some measurement error to them, and then we compute things from them and want to know how much measurement error is there left in those things that we've computed. So a common book for error analysis is this one. I used it as an undergrad in my physics lab, I think it was, and it has this interesting picture on the front of a train that went through a stop at a station and ended up just out on the pavement below. This really happened. This was in 1895 at this French train station, and we'll come back to this story later. Let's switch to paper and pencil. Okay, so like we said, if we know a measurement error or a tolerance on some input variable, let's compute the measurement error or tolerance on the output variable when we're getting the output variable from the input variable via some physics or chemistry or geometry kind of formula. So a straightforward example would be, let's say you measure a temperature of 20 degrees Celsius, and you know your thermometer has an accuracy or precision of plus or minus 0.3 degrees Celsius. Let's convert to Fahrenheit. Here's the formula. If you plug 20 degrees in there, you get 68 degrees. Are we done? Well, we haven't said how much measurement error there is. Just a single number often isn't much good if you don't know how precise it is. So how can we say how much measurement error there is in this? Well, so C is our input variable and F is our output variable. And we might say, how much does F change for a little change in C? Let's write that down. How much does F change for a given change in C? Which is exactly the question that differentials answer for us. How much does Y change for a given change in X, at least approximately? So we could say, what's the differential of F? That would be C times 9/5 plus 32 prime times dc. And what's the derivative of C times 9/5 plus 32? It's just 9/5 times dc. What is C here? dc, it's plus or minus 0.3. So df is 9/5 times 0.3, which is 0.54. So this would be 68 degrees plus or minus 0.54 degrees Fahrenheit. So let's diagram really quick what was going on there. We had Celsius as an input, Fahrenheit as an output. It's a linear function starting at 32 with a slope like that. We were at 20, so we'd go up to the curve and over and get 68. But then we say, well, we aren't too sure about the 20. It really could be 20.3. It could be 19.7. So we'd kind of ghost in some other lines right next to it to show our kind of error tolerance, and then follow those over. And can you imagine how taking a particular width here, putting it through this linear function, will give you an output width. So two copies of this would be like dy or df, and that would just be applying the slope to that. So let's go do that for a more complicated example, somewhat more complicated. I knew this person once who was on a nature walk somewhere in Oregon, and there was a nice bridge, so we'll draw the world's nicest drawing of a pedestrian bridge. And there was a creek down below, world's nicest drawing of a creek. And we'll draw this person in here. And this person, very curious person, wanted to know how far the bridge was above the creek and didn't have a rope or anything. So he decided to drop a rock and time how long it took to fall into the water. So we'll draw this rock dropping at incredible velocity here. And the time it took was 2.1 seconds. And there's a physics formula that says when something is dropping just due to gravity and it's heavy enough that we don't worry about air resistance or anything, it's distance equals 1/2 times g times t squared, where g is 9.8 meters per second squared, the acceleration of gravity. So if you put 2.1 seconds into there, you get, let's look that up. Okay, I computed it. It was 21.6-ish meters. So, you know, that's a fairly high drop. But then the question is, how precise is that? Well, we don't exactly know how much measurement error there was, but human reaction time is in the tenth of a second, tenth of a second or 2/10 of a second realm. They're starting the stopwatch, all kinds of stuff. So let's say it's plus or minus 0.4 seconds. So what's the plus or minus on the distance? So go ahead and compute that using the methods we know. So we would say d distance equals 1/2 g t squared prime times d time. You could use like dt if you want. So that would be 1/2 g times 2t times d time. And what are we going to plug in here? 1/2 times 9.8 times 2 times t, which is 2.1 seconds, times dt, which is 0.4. And you do all that, and you get 8.2 meters or so. So the distance from the bridge to the creek was 21.6 plus or minus 8. Is that the most impressive measurement ever? Not really. But, you know, it was fast and easy. Let's diagram what's going on. So we have time here, not time like as you see it on a calendar or clock on the wall, but time it took to fall, and distance here. And it's basically a parabola. So I'll draw a parabola. And we're operating here at 2.1. So this gives us 21.6. But then we know it's really 2.1 plus or minus 0.4. So we could do a plus or minus 0.4. So we'd be here at 2.5, down here at 1.7. And you can kind of imagine bringing those over. And that gives us, so this value here or here would be dy. But wait a minute, you're saying this value dy is smaller than that one because this is a nonlinear function. And that's true. So let's go look at it on Desmos. So I've got our distance as a function of time formula here. I've got the time estimated from the stopwatch, 2.1 seconds, and that's here. So that's our estimated distance of 21.6-ish meters. And then we've got our error measurement or error estimate of 0.4. So we're showing that as c minus 2.4, c plus 2.4, going up to the curve here, and then over here. And here we're computing those, so the higher vertical distance from here to there is 9 meters. The lower one from here to there is 7 meters. And this differential is supposing that this red curve is a straight line in that region, which is kind of close to true. And it's saying using the slope here and pretending that's a straight line, both of those differential values will come out to 8.2, which is pretty close. So you might be saying, why don't I just do this and get the exact answer? Well, rather than this. Well, this is a much faster way, and especially if you're propagating it through lots and lots and lots of formulas, you want just a single measurement error each time. This value might be, I mean, we haven't really said what plus or minus 0.4 is. It might be like a standard deviation, so there's a fuzziness to the entire distribution anyway. So it's often useful. In homework problems, you might be doing like volume of a sphere, volume of a cone, volume of a cylinder, and there you'd need to find the formulas for volumes. You can just Google them, or there's a page in the book. Let's go back to the railway accident here. You might think that because it was on the cover of an error analysis book, it is a classic example of error analysis, that the engineer forgot to do error analysis and a part failed because it was made too skinny or something. But actually, it was the train entered the station too fast, and they didn't apply the brakes fast enough to stop it. So it really was a human error. And so why is this relevant to differentials now? Well, you could say it's good to keep in mind the big picture. Like, yes, we want to do our engineering properly and make sure all our parts are strong enough to do their job, but it's also good to think about a systems perspective of like, not just will this part do its job, but what is the whole system operating here? There's a whole field of work called automatic train control that's really interesting, and it was first used in 1906, but this crash was in 1895, so maybe that's why automatic train control was starting to be invented in 1906. So it's good to think about calculus. It's also good to think about larger scale issues.